We're going to be looking at rational and irrational numbers today. A rational number is any number that can be written as a ratio of two integers. So if you can write it as a fraction, it's a rational number. To note, when you write a decimal or when you write a rational number as a decimal, it always either ends or repeats. So some examples of rational numbers are like 1/2, so the fraction, 0.8, that's an ending number, -3.4, repeating, a repeating number. All of these are rational numbers. An irrational number is a number that when you write it as a decimal, it never terminates or repeats. And terminates is the fancy word for saying end. So examples are pi, that keeps going on forever. Square root of 2, when you write that as a decimal, it just goes on and on. 3.742542, going on and on with not a repeating pattern. Okay, we're going to practice changing some rational numbers from one form to another today. So when we change fractions to decimals, all you have to do is divide the numerator by the denominator. When you're going to change a terminating decimal to a fraction, so a decimal that ends, you just look at the place value and you place the digits of the decimal over the proper power of 10. So check out if it's in the tens place or hundreds or thousands, etc. And then always reduce. Repeating decimal to a fraction, we're going to learn how to use algebra. We're also going to practice looking for patterns a little bit today. So here are our goals. We're first going to look at 4 examples and just identify whether they are rational or irrational numbers. So I like to just go down to their decimal form often, or first just check to see if they're a fraction. So -2/3, that is a rational number because it is a fraction. If you wanted to check out if it's a decimal form, ends or repeats, it equals -0.6 repeating. So since it repeats, it's a rational number. Okay, our second example here is square root of 15. 15 is not a perfect square. And when we take the square root of 15, we get a decimal that goes on forever without repeating. This makes it irrational because decimal form never ends or repeats. I often just say NEOR, never ends or repeats. Example C, a square root of 100. Well, square root of 100, that equals 10. We know that 100 is a perfect square. Since that ends, it's rational. And then the last one, negative square root of 2.5. You may not know that off the top of your head. You probably don't. But if you type that into your calculator, it's going to go on forever and ever and ever. It never ends or repeats. So it's an irrational number. The next thing you'll be asked to do is to change fractions into decimals. All you need to do for this is divide. So if you divide the numerator by the denominator, you're going to get the decimal form, and you will be allowed to use a calculator. So on A, you're just going to do 11 divided by 12. Your calculator is going to say something like 0.916666. It usually has a 7 somewhere at the end. The only reason the 7 is there is because the calculator rounds. It's really a 6 forever, so double check that rounding. When you write your answer, you're going to write 0.916 repeating. I'm always going to ask you to write it as a terminating or repeating decimal. All right, try the next 2 on your own and then come back and see if you're right. Okay, so this one, 7 divided by 25. When you do that, it's 0.28. And then the last one, a little trickier, 4 divided by 7. You get 0.571428, and then it goes 571, etc., etc. The 571428, that all repeats. All right, this last thing, this is the hardest. We're going to change decimals into fractions. Notice if they don't repeat, you're allowed to just use place value. So there's 0.18. 1 is in the tenths place, 8 is in the hundredths place, and that's all. So it ends in the hundredths place. We say this is 18/100ths. And then we reduce this. 18 and 100 are both divisible by 2. So if we divide them each by 2, we're going to get 9/50ths. Okay. For B and C, these are repeating decimals. We're going to use algebra for this, and this is relatively complicated. So I want you to think about what's going on here, and you might need to use the back of your notes for it a little bit. We'll do 0.37 first. So when we use algebra, we're going to call this number x. X equals 0.37 repeating, both repeating. And then you're going to multiply this by powers of 10 until you get 2 decimal points that are exactly the same. So I'm going to do 10x. If I multiply by 10, the decimal slides over 1, and I get 3.7373 ... Notice x had 0.3737, and 10x has a 737,373. So these decimal points aren't exactly the same. If I try 100x, it moves the decimal point from the original twice. It's 37.373737 ... Okay, if you notice, 100x and just x have decimal points that are exactly the same. They have 37 repeating forever. So these are the two numbers that I'm going to use. And when I use algebra, I'm going to line them up. I'm going to be putting the bigger one on top. So 100x equals 37.37 repeating, and x equals 0.37 repeating. Then what I'm going to do is I'm going to subtract these two equations. So I'm going to subtract 100x minus x, 37.37 minus 0.37. 100x minus x is just 99x. And 37.37 repeating minus 0.37 repeating. The 0.37's repeatings cancel out, so it's just 37. If we want to solve for x, we divide both sides by 99. These are just equal to 1, so x equals 37/99. If we could reduce it, we would, but it doesn't reduce, so we're done. All right, we're going to look at the third example on another slide. All right, we're going to do this process exactly the same way, but in this scenario, only the 6 is repeating. So we're still going to call x 0.916 with the 6 repeating only. So I'm going to, again, multiply by powers of 10 until I get 2 that have the exact same decimal point. 10x, it moves over 1. 9.16, and the 6 is still repeating. 100x, okay, moves over again. 91.6, just the 6 repeating. Okay, right now none of these match exactly, so I still have to go another time. 1000x equals 916.6 repeating. Notice right here, the 100x and the 1000x both have a decimal point that's exactly just 0.6 repeating. So we're going to subtract these two. Start out with 1000x equals 916.6 repeating, and then 100x equals 91.6 with just the 6 repeating. Same process. I'm going to subtract here. I'm going to get 900x equals, and then I'm going to have to subtract, being careful here, 825. All right, so 900x equals 825. I'm going to get x alone, so I'm going to divide both sides by 900. So x equals 825 over 900. This time I can tell there's some common factors, so I'm going to start dividing. Divide by 25 to both. 825 divided by 25, that's 33. 900 divided by 25, that's 36. All right, 33 and 36 still have some common factors, so I'm going to divide by 3. I'm going to get 11/12ths, and that's as reduced as it can go. And if you wanted to double check, you should throw an 11 divided by 12 into your calculator and make sure it really does equal 0.916 repeating, and it does, so you're good.